Hello students, so far we are done with induction motor. Now let us try to understand one of the induction generators, okay, that is Dfig induction generator. Okay, so before going to Dfig induction generator, let us try to understand the operation of motor first. So for motor operation, this is a stator winding, this is a rotor winding. So we are going to supply a 3-phase balanced AC supply to our stator, you know that. Okay, so that will induce a rotating magnetic field in the stator. Okay, I have a stator rotating magnetic field, will induce a stator rotating magnetic field. So at the time of starting, the rotor speed is 0. So this stator rotating magnetic field will cuts with the rotor conductors, that induces a rotor rotating magnetic field. That means okay, there will be a rotating magnetic field in the rotor side also. Okay, the speed of the stator rotating magnetic field is synchronous speed, as well as speed of the rotor rotating magnetic field also synchronous speed. So now our rotor starts rotation, it is speed of nr, okay, in the direction of rotating magnetic field. Okay, so up to this we know, and the difference between our synchronous speed and our rotor speed is called slip speed, and percentage slip is given by ns minus nr by ns. So up to this you know these concepts. Okay, we are supplying the stator is inducing a stator rotating magnetic field, so that links with the rotor conductors, where another rotating magnetic field will be induced, and due to that interaction between the air gap or rotating magnetic field and rotor rotating magnetic field, there will be a rotating force, that is called torque. Okay, due to the torque, our rotor will be experiencing a force that rotates the rotor. Okay, the rotation will be given by nr. Okay, rotor rotation. So the difference between rotor rotating magnetic field and the rotor rotation is slip speed. So up to this we know. Now what we are going to do, and we know that for motor operation, ns is greater than nr. Okay, synchronous speed is greater than our rotor speed. For generator operation, the difference will be nr will be greater than ns. Okay, the rotor speed greater than synchronous speed, then the induction machine is operating as a generator. One more thing, our stator operates at a frequency of supply frequency f, and the rotor current frequency is slip frequency, that is s times f. S is slip here. Okay, you know that, right? Now let us try to understand the torque slip characteristics of our induction generator and induction motor. Okay, so this is the torque slip characteristics of our induction machine. Okay, so here you can see the torque slip characteristics of a motor are between slip equal to 0 to slip equal to 1. So that means this region, in this region our induction motor operates as motoring mode. Okay, that means our rotor speed is less than synchronous speed. That means rotor speed at the time of starting, our rotor speed is 0. So at the time of s equal to 0, our rotor speed will be equal to synchronous speed. So this is not possible in induction motor. So up to this we are trying to get the speed of the induction motor. Okay, the no load speed of the machine will be around this. Okay, so this at this point of torque interaction, okay, if this is my low torque, this will be the operating point of the machine. Okay, so this will be the full load speed of the machine. Okay, so we try to operate the machine at the speed of close to synchronous speed in induction motor. So now when we supply our rotor energy, you know that this is motoring operation. Motoring operation means electrical energy is given to the machine. Okay, machine will deliver mechanical energy. Okay, so electrical energy is nothing but synchronous speed, and mechanical energy is our rotor speed. Okay, let us assume. So in generating mode, when slip equal to negative, that means when slip will be negative, the value of slip will equal to ns minus nr. You know that. Okay, so when this will be negative, when this value will be negative, when the rotor speed is greater than this value. So when 1 minus 2, when as 2 greater than 1, this value will be negative 1. That means whenever our rotor speed is greater than synchronous speed, this slip will become negative. That means in this region our rotor speed is greater than our synchronous speed of the machine. So this is what idea. So in this region our slip will be negative. Okay, so our slip will be negative and the motor will behave like this. This is torque will be negative, slip will be negative, torque will be negative. So this region is called generating region of our induction motor. So induction motor can also be used as a generator for wind generations. Okay, I will going to explain later. So this is generating region of operation. At that time our rotor speed is greater than synchronous speed. As it is generating mode, we supply our mechanical energy to the machine. Okay, so as we supply mechanical energy to the generator, and it will deliver our electrical energy. That means nr is greater here compared to our synchronous speed. That means this is greater, synchronous speed is greater in motor operation, and rotor speed is greater in generator operation. So this is about torque slip characteristics of motor and generator of our induction machine. Okay, and you know that this is a braking operation. Okay, as slip greater than equal to 1, we try to block the rotor of the machine. Okay, when slip greater than equal to 1, that means whenever our speed of the rotor equal to 0. Okay, s equal to ns minus nr by ns. Okay, whenever nr equal to 0, our slip will be 1. Okay, this is at starting condition. Okay, if slip is greater than 1, that will come under braking condition. Okay, so this is about torque slip characteristics of our induction machine. Now let us try to understand our Dfig induction generator. So here is the black diagram to understand the doubly fed induction generator. Okay, as our doubly fed induction generator is a variable speed generator. Okay, it is a variable speed generator because, so you have already seen the induction generator. So there are two types of induction generator. One is grid connected induction generator, another is isolated induction generator. Okay, in grid connected induction generator, our grid will supply the reactive power required by the induction motor. In isolated induction generator, there is a capacitor bank placed on the stator circuit, connected to the stator circuit, that supply the reactive power to our rotor, our induction motor as well as load. You have already seen the videos, right? So now let us try to understand the doubly fed induction generator. Okay, so here we need to have our rotor speed greater than synchronous speed to have our induction motor operate as induction generator. Okay, but in case of our doubly fed induction generator, it is possible to run the machine as generator even our rotor speed is less than synchronous speed. So that is the application of our doubly fed induction generator. That is, it is a variable speed generator. That means our machine will operate as a generator even the rotor speed is less than synchronous speed. Okay, even the rotor speed is less than synchronous speed, our machine will operate as generator, and it will operate as generator even our rotor speed is greater than synchronous speed. So when our rotor speed is less than synchronous speed, this mode of operation is called subsynchronous operation. Subsynchronous generation or operation. Okay, this is subsynchronous generation. So whenever our rotor speed is greater than synchronous speed, this operation is called super synchronous operation. Okay, super synchronous generation. Okay, whenever our rotor speed of doubly fed induction generator is less than synchronous speed, that mode is called subsynchronous generation mode. That means our machine will generate the electricity even the rotor speed is less than synchronous speed. Okay, and it is, if rotor speed is greater than synchronous speed, that mode of operation is called super synchronous generation. Okay, so let us try to understand what is a doubly fed induction generator. So these are the application. One is subsynchronous, another is super synchronous, and it is a variable speed generator. Okay, so generally what is the application of our doubly fed induction generator is, so you know that windmills, right? Wind power generation. Okay, let us assume it is a windmill generator. Okay, so you will be having a gust of wind. Okay, then our windmill rotates. Okay, and this is connected to a generator, that is our doubly fed induction generator. Okay, and you cannot define the speed of our wind so that it will deliver constant rotation to our generator. Okay, so for a synchronous generator, you need to give a constant speed to the generator as mechanical input. Okay, but in case of our doubly fed induction generator, our doubly fed induction generator is a variable speed generator. That means it can generate the power even in the subsynchronous mode of operation, that is when our rotor speed is less than synchronous speed, or in the super synchronous mode of operation when our rotor speed is greater than synchronous speed. Okay, so we don't need to we don't need to rotate the rotor of the machine to generate the power at a constant speed. We don't need to rotate the rotor at a constant speed in Dfig. So that is the best advantage of our Dfig. That means we don't know the speed of wind, right? It may be at a speed of 1500 rpm at one time or 300 rpm at another time. Okay, so we don't define the speed of wind, right? So at any speed of our windmill, we need to deliver our electrical energy to the grid. Okay, so in order to have the advantage of variable speed generation, we are going to place our doubly fed induction generator in windmills. Okay, so as speed of windmills is not constant, we are going to supply a variable speed to our doubly fed induction generator, which generates electricity at any speed of our wind generator. Okay, so this is the application of our Dfig. So now let us see how our Dfig is operating. Okay, so as it is induction generator, it needs some magnetizing current I mu. Okay, its rotor has to be excited, rotor excitation. Okay, rotor magnetization I can say. As it is induction generator, rotor or winding should be magnetized. Okay, so we need to supply some reactive power or some supply to our rotor so that our machine will operate without any problem. Okay, so how it is happening now? Okay, in isolated induction generator, your generator has been supplied with a delta connected capacitor bank. You already seen that, right? It is a delta connected capacitor bank. Okay, you have already seen this, I think. So this is a delta connected capacitor bank, right? This capacitor bank will supply reactive power to load as well as your induction generator. So this is isolated machine. In grid connected induction generator, grid